Hello and welcome back to this series of the cardiovascular system engineering lectures. We are at the third lecture now, talking after a little bit of discussion on the history of cardiovascular models, the terminology, the anatomy. Now we're looking at the fluid dynamics behind the cardiovascular system, and this will be essential to your understanding of how biomedical devices used for cardiovascular disease actually function. So in this lecture, we will be looking at the fluid flow within our vasculature. We'll look at the characteristics of fluid flow, pressure and flow rate. And without going too deep into the topic, we'll try and give you an overall insight into biological fluid dynamics. So let's start. So to start, let's look at a schematic that we actually visited before. And this is the circuitry that goes all the way from the human heart to the other organs, including the lungs. Now, if you remember, we looked at the circuitry in terms of the pressure very briefly, and we realized that the highest pressure is immediately after the blood exits the left ventricle through the aorta, and this is the highest pressure that blood will ever experience, and the pressure will go down beyond this point. So we'll have a decrease of pressure as it goes through to the other organs and gets circulated back into the heart, where here we have the lowest pressure as it enters the vena cava, and then as the right ventricle pumps it into the lungs, we have an increase of pressure, and then again as it goes through the lungs, it's going to lose its pressure, and therefore it needs to be repressurized and pumped back into the circuitry. So the reality is that whenever you go from the heart towards these capillaries in the organs, you're going to have a lot of waste of energy, basically, because of all the resistance involved in this network. And that's why it needs to be pumped back and pressurized. So this is mainly the gist of what we're going to look at today, is these variations of pressure and flow rate. So to look at this from a more technical perspective, it's essential to understand the difference between these two parts of the cycle, systole and diastole. So these two are the two main phases, and there are lots of sub phases in each of these, but the main idea is that in diastole what happens is that the atrium in both sides, both left and right, in sync pretty much, are feeding the ventricles, and so you have an expansion of the ventricles pumping into the ventricles, and then in systole the signature is the fact that they're getting contracted and pushing the flow out either through the pulmonary arteries or through the aorta to the rest of the body. So this the squeezing action here that happens makes it so that there are two phases here for this pumping action of the heart. And in other words, this is the filling phase, and this is the pumping phase. And so in each of these phases, you have a variation of pressure and flow rate and volume, as we will look at in a minute. So let's see. So this is a good animation showing the same process. So you see that in part of this cycle, which we call it the cardiac cycle, the atria are actually squeezing blood into the ventricles, and then at another section of the same cardiac cycle, what happens is that the ventricles are squeezing the flow out and in through the aorta or the pulmonary arteries to the organs. And an interesting feature here is that the first phase, where you're squeezing your atrium, either left or right, the valves open, and these, if you remember, are your atrioventricular valves that connect the atrium to the ventricles. And in this case here, it was the mitral valve, if you remember, and this was the tricuspid valve. So these two open to allow the blood to flow into the ventricles. And then these two valves are one-way valves, so they're actually going to block the flow in the other way, in the other direction. And so whenever these two ventricles start to squeeze and contract, they're only going to pump the blood through to the aorta or this pulmonary artery here, and it's not going to go back to either of the atrium. So this is basically the two phases of, again, systole and diastole, as mentioned in the previous slide. Now, to look in a bit more detail here, this is the sort of a more accurate plot of the variations of pressure and volume in the ventricles. So what you see here is the volume of the ventricle is constantly changing, so is the pressure of the fluid within the ventricle. And so these two, if you look carefully, they're pretty much the inverse. So wherever you're seeing an increase in pressure, that means it's being squeezed, and so the volume is being reduced. And wherever you see a reduction in pressure, the volume is actually increasing, or in other words, it's expanding. Now, we're going to look at this in a bit more detail because there are some regions that are a little bit trickier to understand. Like this region, for instance, where the volume stays the same, but you have a significant drop of pressure. Similarly here, where the volume stays the same, but you have an increase in pressure, which we call it isovolumetric contraction or isovolumetric relaxation. Now, to understand this better in more details, I've divided this into multiple sections. The first section is here, and what happens here is we're looking at the beginning of the basically the filling phase, which was the diastole. And what's happening is that the volume of your ventricle is increasing. Okay, the volume is increasing because we're filling it with the blood. In other words, the pressure is also increasing in this phase, right? We are filling it with blood from the atrium, and therefore the volume is increasing, so is the pressure. And at this point here, the valves close. So this is the valve that connects the atrium to the ventricles. And what's happening is that in this phase, that valve closes, so that whenever the blood has filled the ventricle, it can no longer go back into the atrium. That's what the valve does. As I've mentioned before, it's a one-way valve. So now that the blood has filled your ventricle and the valve is shut, the volume has to stay the same because, of course, blood is incompressible. So the volume here stays the same, but the muscles in the periphery of the ventricle are now contracting. So they are trying to squeeze the blood and pressurize it. And that's why at that same constant volume, and the valves are all shut, the pressure goes up. So they're squeezing and pressurizing it, so that as soon as the valve is open, and this time I'm referring to the pulmonic valve and the other valve there, the aortic valve. Once those two open at this point, it ejects the blood. And so the two phases that follow are first the isovolumetric contraction, that pressurizes the blood, and suddenly, as soon as the valve opens, it's going to burst out in the systole part of the cycle. And after the blood is then pushed through the aorta, what's going to happen is you're going to have another isovolumetric phase, which is now relaxation, where it loses all that pressure and it goes back to the relaxed ventricle state and gets ready for the next cycle. So this is when the valves again open, and this time what's happening is the inverse flow happens and it gradually relaxes in the continuation of the diastole cycle and gets ready for the next pumping cycle. So that's looking at it at a more granular level, but again, there are loads of details associated with this. If you look at more accurate plots, and if you zoom in, even in this one, you'll see there are ups and downs that are more granular. And these are all, none of these are accidental. They're all signatures of a certain event in this cycle. But for your general understanding today, this level of detail is good. And just make sure you understand these phases very well. Now, it's interesting that if you look at that plot for different individuals, depending on their age, depending on the level of exercise that they have, you'll see a different rhythm, basically. You'll see a different pressure or volume waveform. And in this case, you can see that as you get older and older, what happens is that generating the same flow rate, your pressure difference goes much higher. And what this shows here is the area under this curve is the amount of work done by the heart. Okay, and now this area under the curve, basically in this case, is a lot larger than what you have in a younger individual, right? To be able to achieve the same flow rates or the same efficiency, you have to do a lot more work. And in this case, again, you see a similar situation. To generate the same amount of oxygenation flow, you actually have to do a lot less work in a more efficient heart. So when you put various individuals under these measurements, you'll see some very distinct waveforms show up, and that is based on their lifestyle and their age, and a lot of the variations that have happened either anatomically, genetically, or otherwise environmentally in their cardiovascular system. The next important thing which we should look at is the fact that as blood gets pumped through the aorta to the organs and back, there is, again, a pulsatile nature to the pressure and flow rate of blood. That's exactly the same pulse signature that you saw before. But then the interesting part is that, first of all, you should know that when we've got rather large vessels, such as the aorta or the arteries, because they're significantly large, the flow isn't a unidirectional flow, and the velocity profile is something that varies across the radius. When you get to smaller capillaries, you have a more uniform laminar flow, but in larger ones, such as the aorta and the arteries, you have a velocity distribution, and the flow directionality isn't unidirectional. So you can have circularity to the flow, you can have vortices in some regions, and those are actually causes for various cardiovascular disease. Now, what happens is that as the flow develops through these larger vessels all the way to the small capillaries, this three-dimensionality and variation in flow starts to go away. And so in the capillary level, it becomes more unidirectional because they're so thin, the flow is laminar and unidirectional. But then beyond that, there's another part too. Apart from flow rate, the pressure distribution, which you saw in the previous plots, had its own distinct look for every individual. That is also going to get dampened away. So what happens is that you'll see that this waveform, as it travels through, it dampens to become a uniform pressure drop as it gets to the capillaries and then through the veins. Now, as you can see in this plot, you start with significant variation in the pressure, and this is the mean value. But then as you go forward all the way to the arterioles and then the capillaries, you see that that vanishes. The reason this happens is all these larger vessels before the capillaries are actually very compliant. They're very soft. And so they act like a damping mechanism, like a damping system in your vehicle, such as a pressure cylinder piston system, where the fluid inside this elastic spring-loaded system is actually damping the impact. Now, what's happening here is similar. These are acting like a big flexible sac, and so the liquid entering it, the blood entering it, may come with a really rather random flow distribution, a very you could say non-laminar nature, and then this turbulent flow, as it goes through the compliance of these tubes, gradually straightens up and becomes the energy of it becomes damped through the walls of these vessels. And as it goes and gets through to the capillaries, it becomes more of a laminar flow, which then follows through to the veins. And at this point, you have a very much uniform and developed flow. Now, this is really important to know as well, because shear stress and flow rate have a significant influence on the cellular behavior of these blood vessels, as we'll see, contribute to a lot of these diseases. They are the major key players in a lot of the disease. So the last bits of information, again, as I mentioned here, this is another demonstration of what I said, which is it doesn't matter what age you're at, but as it travels from the aorta to the downstream vasculature, you'll see changes in that profile there. And so you'll not only see the oscillatory and pulsatile motion going away, but you'll also see the waveform changing as it travels through. And what you see here is, again, the two phases, the systole and diastole, and this is the left ventricle as it pumps blood through the aorta. And the factor I was, just telling you about, which is the compliance of the aorta and the larger vessels, is what damps and absorbs that energy of the fluid, making it more and more uniform and collinear in terms of its streamlines when it enters the capillaries. So the reason we have a steady state flow in the capillaries is this compliance and the compliance of the arteries and the laminar flow that then happens in the capillary level. And why is it that this steady flow is desirable in the capillary level? Because we actually need that. We need to have, we'll talk about this extensively, how the dwelling time at the capillary level is critical and how it's maintained. But basically, the steady flow is what allows a uniform and time invariant delivery of the nutrients and gas, the extraction of waste, and also enables heat transfer. So now moving on again to another part of this, it's interesting to look at the distribution of blood flow. So as you probably remember from the previous lecture, when we were looking at the anatomy, of the cardiovascular system. The blood that goes through the aorta gets divided into many sub portions. One that goes, for instance, to the carotid, the common carotid artery, one that goes through to the arms, and one that goes and follows through to the other organs, for instance, the kidney or the liver, the kidneys or the liver. And what happens here is that each of these organs have a certain requirement for the amount of circulation that they want to receive. Here, for instance, you see that the circulation, the renal circulation that happens is about 1100 milliliters a minute, whereas, for instance, your skin requires only a 500 milliliter per minute chunk of that overall about 6,000 milliliters per minute blood flow. And so the overall percentage for each of these organs is quite different. So here, for instance, you have 4% is only consumed by the heart itself in the coronary arteries, whereas the brain actually uses about 13%. These are very interesting figures to look at the metabolic rate and also the uptake of blood and oxygen in different organs. And the way that this is controlled is by the shape and the geometry of the blood vessels, but also the resistance of the vasculature downstream in those organs is what determines how much of the blood goes through each stream and each path. And when it comes to the veins act like a reservoir, and what they do is they store all the excess blood coming through the outlet until it's then pressurized through the right ventricle. And this is also interesting. It shows how much of the blood volume in each cycle as it's traveling through, how much of it actually is stored at every point of time inside the veins, and how much of it is stored in the arteries, for instance. And you see that a major portion of it, a big chunk of it, is actually about 64% is in the veins at every point of time. Now let's look at fluid dynamics in a blood vessel. And this is a really important part. I really want you to understand this very well. When we're looking at a blood vessel, we have, again, as you've seen this multiple times, two important variables: the pressure drop and the flow rate. So delta P, the pressure difference, and Q, the flow rate. And just like a resistance in an electrical circuit, you can look at it from this perspective of current or flow rate multiplied by the resistance of that, let's say, channel or blood vessel, is equal to the voltage, or in this case, the pressure drop between the two ends of that element. So just like a resistance that has a current running through it and the voltage difference between the two ends, and this is the equation that relates those. In a channel, you can say the pressure difference from the inlet and outlet is the product of the resistance of that channel and the flow rate. And again, based on Poiseuille's law, Poiseuille's flow model here, we actually know that resistance is the product of viscosity, the channel length, divided by the fourth power of radius. Now, what this means is that, for instance, if I increase the length of my blood vessel, the resistance is going to go up. That makes sense, right? Because you're going to have a greater pressure drop from the inlet to the outlet. If you have a 10-meter channel versus a 1-meter channel, of course, it's going to have, a lot more pressure drop from the inlet to the outlet because you're going to have a lot more resistance. Similarly, if you reduce the radius, make it smaller and smaller, the blood or fluid, whatever it is that's traveling through this, has to use a lot more of its energy because all the friction with the walls is going to actually lose a lot more pressure as it travels through. And it's interesting that it's proportional to the fourth power, meaning that if you reduce the radius by a factor of 2, you'll see that resistance will actually increase by a factor of 16, which is crazy. So that's why capillaries are going to actually consume significantly larger, significantly greater amounts of energy than the arteries and arterioles, okay, because their radii are significantly smaller. So it's both the length and the diameter or radius of these blood vessels that matters when it comes to the amount of pressure loss or resistance, which are proportional again, that the blood experiences as it travels through these. Now, based on that, we're going to look at a couple of arguments and we will conclude today's lecture. The first is, why do we need fluid flow? Why isn't Aristotle's model sufficient? Meaning that you just fill the body with blood and it has all the nutrients, and the nutrients can, well, the nutrients in that case would have to diffuse. Now, the most basic and cheapest way to initiate transport is through diffusion. And diffusion is a passive mean of transport, and it's the idea of molecules moving from one point to the other because of a difference in concentration. It's extremely slow. It's extremely slow because the molecules have to move through the solvent or the solutions environment, and it takes a long time, and it's just not efficient enough when it comes to longer distances, right? So the idea is that as important and significant the role of diffusion is in our organs and in our body, it's just not efficient for the long distances. The reason is that the diffusion distance, if you look at this equation, it says the rate of diffusion is proportional to the surface area. So if you increase the exchange surface area, it's going to diffuse faster. The concentration difference, of course, if it's greater, then it's going to diffuse faster. And if you then change diffusion distance, it's also going to then have an inverse effect, because if you make it longer, then it will take longer, so the rate is going to be reduced. So for the molecules to diffuse, these are the three variables, and we've already gone over this in the previous modules that you've had last year. But basically, diffusion works well if the surface area is large, or if the diffusion distance is very small, then the rate is okay. When you actually have long distances, to achieve effective transport, you need to have bulk fluid flow, meaning convective and convection flow. So that's the first bit. But then why is it that we have all these variations? So why can't it all be arteries? Why should it vary all the way to capillaries and then all the way back? So the reason we have this range of diameters is, again, going to go back to Poiseuille's law. We know that fluids have to circulate, right? Because our lungs, our other organs, they all need blood. So it has to circulate to deliver all of those. But when it gets to the exchange sites, okay, when it gets to, let's say, the organ of interest, these vessels require to have a larger exchange area, right? That's because the exchange area at the organ level, now it's using diffusion to go from the capillaries to the bulk of the organ. The surface area is what determines how efficient your diffusion process is. Now, you may say that, okay, so if we know that capillaries have a larger surface area to volume ratio, and the reason for that, of course, is, the same reason we use nanoparticles for drug delivery or microparticles for drug delivery, because the surface area to volume ratio increases as you reduce the size of an object. Okay, so you may say, why don't we just use capillaries? The entire network can be just capillaries. The answer there is that if it was all capillaries, what would have happened was that this resistance would have been crazy, right? So if you had capillaries going all the way from the brain, the heart to the brain, from the heart to the lungs, from the lungs back to the heart, and then from the heart to the other organs, you'd had a very long network of tiny vessels, very inefficient when it comes to the energy of the fluid. It will all be wasted because of these highly resistive network elements. So that's why we have larger vessels to carry these to places far away, to the extremities of our bodies. And then once it reaches that destination, it then branches to enable a greater surface area, larger surface area, and a better exchange at that site. And now the last question here is, how does this reduction in vessel size, all the way to capillaries, affect the contact area and the exposure time? The exposure time is the dwelling time, the time the blood is actually in contact with the tissue, okay? The reality is that what happens is, when you reduce the size of a vessel, going all the way from arteries and arterioles to capillaries, when you reduce the size, what happens to the speed? You know that the conservation of mass, in this case, tells us that the volume coming in through here should stay the same there. If the density hasn't changed, this volume should remain the same, meaning that if your area is reduced, because the product of A1 times V1, velocity at point 1, is equal to A2 V2, if the area is reduced, the velocity will have to increase. What does that mean? What it means is that the blood that goes from the arteries and arterioles to the capillaries is speeding up. Speeding up means that it spends a lot less time, actually proportional to the second power of the radius, less time in the organs, which isn't good because it requires time. It requires time to exchange, right? It says that the fluid or the blood should spend a significant amount of time at the exchange site so that it can actually exchange the nutrients, the waste, the oxygen, and heat. So this actually is the inverse, right? When we go to capillaries, we've got an issue. So we know that the cross-sectional area overall, when we go to capillaries, must be larger than when we start from arteries and arterioles, because we want to spend more time in those regions. But the question is, does this happen in reality? Now, we've looked at some very basic equations, but when we meet on Thursday, we will put all of those together and we will look at the branching that happens when you go from a larger artery or arteriole to a capillary. And we will try and understand how the radius evolves from the mother branches to the daughter branches, and whether or not this is actually true, that the overall cross-sectional area is going to be greater at the capillary level than it was at the stemming initial artery and arterial level. And we will try and see how the relationship between the daughter vessels and the mother vessels are actually derived. That will basically allow us to produce specific designs for bifurcations if we're actually trying to 3D print or produce a model of human vasculature or an organ, or if we're actually going to produce a stent that's a specific type to fit a certain bifurcation. And knowing this relationship between the fluids and the geometrical, the fluid properties, the speed and the pressure and the viscosity, and the geometry of our vasculature, we can then start designing and selecting designing devices and selecting materials for these applications as we move forward. So this sort of sums up our understanding of the anatomy, the function, and the fluidics, as well as the physical model of circulation in the vascular network and the cardiovascular system. And now we are ready to move on to cardiovascular devices, implants, and diseases. So in the next lecture, we'll be talking about various cardiovascular diseases, and then we'll get to the exciting part of what are we actually doing to treat those diseases very soon in next week's lectures. So until then, I hope you've enjoyed this lecture and energetic to move forward. Have a great rest of the day and take care.